Hello. I am Tina, Tank's full-time natural language processing bot. In this episode, I will be reading from science writer Martha Henriques' piece Order and Chaos. In the piece, Henriques investigates new theories of time developed in quantum physics. Grappling with these theories forces us to abandon our intuitive sense of how things are, and enter into the strange poetry of nonsense that comes from the most beautiful mathematics. Each tick of the clock, twitch of the second hand or shifting light of your phone gives us something absolutely necessary. This is where we find the basic building blocks we need to construct the architecture of our lives, what we do, where we go, who we meet. These building blocks are the seconds, minutes and hours that make up our experience. None of what we do in life makes sense without an element of when. The problem is that these blocks, the essential seconds that we live by, are a figment of our imagination. The universe exists instead in a crash of events piled in chaotically with no meaningful sequence. The temporality that we perceive is not a thing that can be pinned down, dissected mathematically and therefore understood by physics. At least, not according to loop quantum gravity theorist Carlo Rovelli. In his latest book, The Order of Time, Rovelli reminds us that the closer we peer into matter on the tiniest scale or the further we stare out into space, the less we can make sense of time. The now we experience on a summer's night lying on the grass looking up into the sky is not the same now as the star at which we are gazing. That star, say, V762 Cass in the constellation Cassiopeia, one of the most distant stars we can see with the naked eye, is 16,308 light-years away. What we see are historical images of past celestial bodies painted on the backdrop of black space. Each bright spot is alone and distinct in its own time frame. If we were to take a step deep into space, perhaps close to the heart of the Milky Way, we would discover for ourselves another way in which our concept of time disintegrates. Here, we find a supermassive black hole. For this experiment, we wear two precise watches, one on each wrist, set to the same time. We turn our eyes away from the black hole and stretch our left arm as far as we can towards it. Our right arm, we stretch as far as we possibly can away from it. For a few moments, we stay here, arms outstretched. Bringing our arms back to our chest, we consult our watches. Our perfectly synchronized watches no longer show the same time. Albert Einstein's general theory of relativity explains why. Very large and massive objects like black holes distort the fabric of space-time. One consequence of this is that time becomes dilated depending on where in the gravitational field it sits. The watch held close to the black hole is now running slow. Less time has passed for our left hand and its watch than our right. These effects are most pronounced near an extremely large entity like a black hole, but even here on Earth, with the most precise possible clocks, the same effect is measurable. In 2010, in a laboratory in Boulder, Colorado, two atomic clocks placed one above the other measured the dilation of time due to the Earth's gravitational field. The clocks were not even a handspan apart, at an elevation of just 30 centimeters. Even at this distance, the difference in the passage of time between the two clocks was clear. The physics that works for very large things is notoriously difficult to reconcile with the physics of the very small. Tiny things, like subatomic particles, exist according to entirely different rules to planets and stars. But in terms of how both kinds of physics destroy our simple concept of time, they are almost equal. As above, so below. The most striking thing about modern quantum physics is how mind-bogglingly little sense it makes on an intuitive level. None of us has been in two different places at the same time or jumped in and out of existence even for a moment. This poetry of nonsense comes instead from profoundly beautiful and elegant mathematics. On quantum scales, not seconds, milliseconds or nanoseconds but units of time far, far smaller, time is not the smooth, continuous passing line that we think of it. As Rovelli tells us, in this miniaturized world, everything is granular. Time as well as matter is divided into units so small as to be indivisible. There is a moment so brief that there can be nothing that lasts for less time. And just like other quantum phenomena, these fractions of time can be superimposed, can jump in and out of existence, and can change depending on who is observing them. For a moment, leave this impossibly small world where time behaves in unimaginable ways. Zoom back to the comforting, familiar scale of Newtonian physics, one of the best ways to understand the nature of medium-sized bodies, like us. Perhaps here, in the mathematical equations that govern the world as we know it, we can find something solid that means that time has to exist on our level. What about the most sensible physical law we know? Still things stay still unless they are pushed or pulled by something. Things that are moving stay moving continuously in a straight line, unless they are pushed or pulled by something. Can we not prove that time exists by this rule? A billiard ball sits still on green baize. The tip of a cue collides with it. The ball travels on in a straight line until it crashes against another ball, which ricochets away. Again, we soon find ourselves clutching at nothing. Rewind the video of the billiard balls. Take the snapshot of the two balls colliding and zoom in until all you see is one coming into frame and pushing the other out. Rewind. Now play forward. There is no way to tell which way round is the original, which is the reverse. It's only from the context, the bigger picture with the cue that pushes the ball, that you can divine the sequence of events. There is no way of telling past from future here. With this symmetry of past and future, the idea of cause and effect itself melts away. The only hint of where time might appear, might prove to us that it is real, is hidden in chaos. One of a series of rules known as the laws of thermodynamics could help us. This is the law that states entropy, or disorder or chaos, always increases. You cannot go from more chaos to less chaos, overall. Take an egg. That is a neatly ordered system, yolk, within white, within shell. Smash it. Yolk, white, jagged bits of shell everywhere. Try winding that film back. You can always tell what comes first. The whole egg becomes the mess of jellified liquids. You cannot throw a mess of broken egg in a bowl and watch it become whole. Perhaps here, in the creation of chaos from order, we have found a signature of time, the reason why it always appears to point in one direction only, forwards, passing forever from the past into the future. This is the sense of moving from a world of higher order to one of less order, more chaos. Constantly, throughout life, the act of living, of existing, brings you further into this world of chaos. As entropy increases, time passes. So perhaps the passage of time is the growth of disorder from an ordered world. Minutes, seconds, milliseconds are all tiny slivers of chaos finding their place in our world. Ravelli has an answer for this, too. Chaos and order, he says, are in the eye of the beholder. What is disordered to one person makes perfect logical sense to another. You may wish to arrange a series of red and green balls by color, Ravelli suggests. Your friend may be colorblind, and to her, it makes much more sense to arrange them by size. Which arrangement is the ordered one? Which the chaotic? Perhaps our perceived increase in the entropy of the universe is, in fact, an aesthetic perception. It is only this view, interpreting order and chaos in our surroundings, that makes the past seem any different from the future. As Ravelli said in a recent lecture at the Royal Institution in London.
We are a special subset of the universe that interact with the rest of the universe in such a way that the past looks ordered to us. What is special is not the universe, is a subset of the universe to which we belong. This is called the idea of the perspectival origin of entropy, and I think it could be an ingredient for understanding why the past is different from the future. There's nothing special in the early universe. It's special the macroscopic, the coarse graining that we do.
Here, Ravelli must turn to neuroscience, an area he acknowledges is beyond his expertise, to explain how time might, in fact, be an effort of our own creation. It is down to our brain, he posits, to clutch at passing moments, order them and pull some sense out of their sequence. In other words, it could be that we are, in fact, time machines. At last, we reach a point where we have an inkling of intuition. Time does, after all, change depending on our mood. Neuroscientists have clearly shown that in our mind's eye, time really does fly when we are having fun. It also flies when we are in control of our fate, the author of our own actions. It drags when we are bored, and when we are controlled by others. Time is lost, wasted, gained or spent. These are all human activities. The way we think about time and relate it to our lives is personal, human and emotionally charged. Our time is what we live for, as well as what we live in. We scurry to make sure we're not late, We try to look older or younger, we gather experience, we travel forwards in our wishes for tomorrow and backwards in nostalgia. When we pause to think about it, of course we are time machines. The harder we look into physics to tell us the real nature of time, the less we find ourselves convinced of its existence. The concept of time becomes dissatisfying, empty and eventually meaningless. It is in our thoughts and our emotions that the meaning of time, and our understanding of it, returns to us. To hear more podcasts from Tank, subscribe on iTunes or follow us on SoundCloud.